Hello elements, welcome to Unit C review. Unit C is chapters 8, 9 and 25. Chapter 8 primarily deals with types of bonding, lattice energy, bond enthalpy, Lewis structures, while chapter 9 goes more 3D aspect of the molecule structure, how are they arranged in real life, so via CPR, hybridization, and then chapter 25 is organic chemistry. So let's continue our review for Unit C. So at the heart of Unit C is chemical bonding. And chemical bonding refers to generally intramolecular bonding, meaning how do atoms bond together to form a compound. And this intramolecular or interatomic bonding is of 4 types. Ionic bonding, covalent bonding, metallic bonding, and covalent network bonding. Ionic bonding occurs between a metal and either a nonmetal or a polyatomic ion, and ionic bonding involves transfer of electrons. Covalent bonding is characterized by the absence of a metal. For example, P2O5, HCl, all of these are covalently bonded, and you can identify that because there is no metal present. And covalent bonding is between nonmetals, and it is characterized by sharing of electrons. And how electrons are shared again makes types of covalent bonding, and I'm going to go in detail in a minute on that. But let's go here to metallic bonding. This type of bonding is present in pure metals, and this is called electron C model. An electron C model of metals is where you have a bunch of positively charged nuclei that do not hold on very tight to their electrons. So electrons have the freedom to move about. So it almost seems like electrons are present, a sea of electrons is present with positively charged nuclei. And these electrons are called free electrons. And because these electrons are free to move about, the metals are good conductors of electricity. And they are malleable because their orbitals overlap, so if you stretch them or hammer them into a sheet, they can be done. Now, covalent network is a network of covalently bonded atoms or compounds. So covalent network is a network of covalently bonded atoms or molecules. And the examples of these you pretty much have to memorize. Examples are quartz, silica, germanium, silicon, graphite, diamond. All of these are covalent network solids. And the thing that's very special about covalent network solids are they are insoluble, because these are such large conglomerate of either molecules or atoms that they are very stable. They have very, very high melting boiling points, and they are generally insoluble. At this point of time, I'm going to move a little bit away from the concept map, and I wanted to clarify a concept that I still see lacking. And that concept is the difference between inter and intramolecular bonds. So you know that intramolecular bonds are these 4 types: ionic, covalent, metallic, covalent network. And intermolecular bonds are hydrogen bonds, London dispersion forces, dipole-dipole interaction. And separately you get them, but let's say I ask you which bond is stronger, ionic or covalent? Generally kids will say, well, ionic is stronger because NaCl has a high melting point as compared to water. I want you to understand when you are melting NaCl. NaCl is an ionic solid, right? So it is present in form of a lattice. And in the lattice there are forces of attraction that are holding them together. So when you are melting NaCl, you're breaking ion-ion bonds. But when you are boiling water, HOH, right? So this is one water molecule. Let's take another water molecule. Now, hydrogen bonding exists between negatively charged oxygen and positively charged hydrogen. When you are melting NaCl, you're breaking ion-ion bonds. But when you are melting ice, you're only breaking hydrogen bonds. You do not separate hydrogen and oxygen and hydrogen atom during melting, correct? Water molecules are just separated from each other. That's what's happening during melting. You're making them go far apart. So you're breaking intermolecular force. I want you to keep that in mind and remember that distinction between intra and intermolecular bond. And by an extension of it, that is why the melting points of covalent network solids is so high, because when you are melting a covalent network solid, you're actually breaking a covalent bond. All right, now coming back to ionic bonds, let's elaborate a little bit on ionic bonds. Ionic bonds, I want to talk about strength of ionic bond. And strength of ionic bond is determined by something called as lattice energy. And lattice energy is defined as amount of energy required to break 1 mole of a solid ionic compound. Let's take, for example, NaCl. To break it into its ion in gaseous state. That's how lattice energy is defined. And whatever energy is required, this is called lattice energy. Lattice energy is also directly proportional to the charge of the two ions and inversely proportional to the distance between the nuclei of two atoms. So the larger the atoms, the greater the distance, the smaller the lattice energy. The higher the charge, the greater the lattice energy, greater the strength of ionic bond. Now, one way to calculate lattice energy is by using the lattice energy equation. Other way of calculating lattice energy is using Born-Haber cycle. So, Born-Haber cycle is almost like Hess's law together. You put different equations, then you arrange them in a way that you get the equation that you want. So if you want to calculate lattice energy for, let's take example of sodium chloride, ultimately the equation that we are desiring is NaCl solid is being broken into Na plus gas plus Cl minus gas ion, and we are interested in delta H, or heat of formation for this, and that is the lattice energy here. Okay, to get that we can employ various equations. Let me write them in different colors so you don't get confused. The first step in forming sodium chloride into sodium ion and chloride ion would be, you'll take sodium atom which exists as solid in ground state, and you'll have to change it to sodium atom in gaseous state, and this will be heat of formation of sodium gas. Similarly, you'll have to take a chlorine molecule which is in gaseous state and break it up. So take half a chlorine molecule and break it into gaseous chlorine atom, and we'll call it delta HF of chlorine gas. The third step would be, now from this gaseous sodium atom, we remove an electron and form it into an ion. And the corresponding energy change is called first ionization energy of sodium. Remember, that's how first ionization energy is defined. Similarly, to the chlorine atom, we add an electron which changes to chloride ion, and we call it as first electron affinity of chlorine. And ultimately we have everything else, but if we look at definition for heat of formation of NaCl, how is that defined? That's defined when 1 mole of solid sodium chloride is formed from its elements in their natural state. Now remember, sodium's natural state is solid and chlorine's natural state is gas. So to get the above equation that we need, you add 1, 2, 3, 4 and you reverse the fifth. So if you add 1 through 4 and subtract fifth from it, it'll give you this equation. So this method of calculating lattice energy is called Born-Haber cycle. Moving on, I'm going to go back now and focus a little bit more on covalent bonding. So I'm going to scroll down the screen. And I'm going to go from current slide. So I'm continuing on from covalent bonding. Covalent bonding refers to sharing of electrons. And if electrons are shared equally, you have what's called non-polar covalent bond, and this type of bond happens generally between the similar atoms when the electronegativity difference is between 0 and 0.3 electronegativity difference. The second could be that the electrons are shared unequally, and when they are shared unequally, it results into either a polar covalent bond where electronegativity difference is generally between 0.3 to 1.7, or it can form a coordinate covalent bond. Now, non-polar covalent bond can occur between nitrogen, oxygen, hydrogen, and non-polar covalent bond can be a single bond. Actually, even polar or non-polar, the covalent bonds, let me write it here, that's a better place. Covalent bond can be single or double or triple bonds, right? So they can share up to maximum of 6 electrons. And single bonds is the longest bond, but it is the weakest bond. And triple bond is shortest, but it is the strongest bond. And how do you calculate for single, double, or triple bond? Bond enthalpy. Bond enthalpy is written as delta H reaction, and it is almost the opposite of Hess's law, where it is summation delta H of bonds broken, which is for reactants, minus summation delta H of bonds formed. For example, if we had a reaction CH4 plus Cl2 gives you CH3Cl plus HCl. In this case, you are making 1 mole of CH bond, you're breaking 1 mole of Cl-Cl bond, and you are forming 1 mole of CCl bond, and you're forming 1 mole of HCl bond. So delta H will be here, bond broken, so delta H of CH bond plus delta H of Cl-Cl bond minus delta H of CCl plus delta H of HCl bond. So in these type of problems, be sure to write out the expanded structure or structure formula so you can see clearly what bonds are breaking and what bonds are forming. Now with the polar covalent bond, you form a polar molecule, and polar molecules generally have dipole moment. And remember, how do we draw dipole moment? If it is HCl, then you draw it from positive to negative. If you have ammonia, if there are multiple polar bonds, then you draw individual polar bonds, and then you will draw the overall polar bond showing the overall polarity of the molecule. And then coordinate covalent is generally in Lewis acids and bases like ammonia and BF3. When they combine, they just form BF3NH3, where ammonia lets BF3 use its lone pair of electrons. So this lone pair that's given only by ammonia is shared equally by both. And this is generally found in Lewis acids and Lewis bases. Okay, now moving on to covalent compounds and Lewis structures. Okay, so covalent compounds or covalent bonding, I'm going to overlap here. It leads to covalent compounds, and generally covalent compound structure, 2D structure, is shown by Lewis structures. Lewis structure, even though primarily they're used for covalent compounds, can be used to show the structure of ionic compounds as well. For example, how would you show the structure of NaCl? Using Lewis dot diagram, you'll draw sodium as an ion, and you'll draw chlorine with its complete octet because one of the electrons is transferred as an anion. Now, how do you draw Lewis structure? Remember, go over the steps. First, you figure out how many valence electrons, how many does it need to be happy, number of bonds, then you do a counting, and then you draw structure. For example, ammonia's Lewis structure will be 3 single bonds and a lone pair on nitrogen. And here, this Lewis structure, you guys are pretty good with it, so I'm not going to go over it in detail. So you should know how to draw the Lewis structure. Remember the exceptions: hydrogen and helium are happy with 2 electrons, or they're duets. Beryllium is happy with 4. Boron is happy with 6. But these are generally electron deficient species, and they are actively looking for electrons. In the exceptions, you must also remember NO and NO2. These are odd electron species. So when you add up the valence electrons, you'll get an odd number. So remember, even though you have 1, you will consider it as taking up 1 orbital. So when you are adding how many does it need to be happy, you'll almost count it as 2. Now, what's special about odd electron species is these are highly reactive. If there's a NO2, it will seek another NO2 out and form N2O4, which is very stable. So NO2 is very unstable, N2O4 is very stable because that single electron has now paired up in N2O4. This process is called as dimerization. And dealing with Lewis structure, we have another concept which we call as formal charge. What is the purpose of formal charge? First of all, formal charge is an imaginary charge. It's not a real charge, it's an imaginary charge. And the purpose of formal charge is to figure out correct Lewis structure. How do you figure out correct Lewis structure using formal charge? First of all, that you want to get formal charge of closest to 0 on all elements. -1, +1 are both charge of 1. Second, you want to give more negative formal charge to more electronegative atom. And lastly, how do you calculate it? To calculate formal charge, it is how many valence electrons are present in an atom in uncombined state, and then how many electrons are given to that atom in the combined state. To calculate the electron on the atom in combined state, the lone pairs belong to that atom and half the bonded pairs belong to that atom. And the difference of the two gives you the formal charge. Remember, formal charge is given to each atom. It is not for the whole molecule, but for each atom it will have a formal charge. Then another thing is, if an atom or a molecule can have more than one structure with correct formal charge, then we call that phenomenon as a resonance. So what is resonance? Resonance is when more than one correct Lewis structures are possible. Correct Lewis structures possible. For example, a telltale sign is when there is a traveling double bond. For example, in carbonate, this double bond can be present on either of the three carbon-oxygen bonds, and because they all will have the same formal charge, we call it resonance structure. The last concept here is bond order. Bond order is the number of single, double, or triple covalent bonds that are present between two atoms. It is pretty simple to figure out. Here in ammonia, bond order is 1, but carbonate, where you can draw 3 possible resonance structures. I'm just drawing the skeleton of those resonance structure. I haven't completed the octet. Here the bond order will be, you add up all the bonds between any specific position. So 4 bonds between 3 positions, so 4 by 3, or its bond order will be 1.33. Now let's move on more to chapter 9 of Unit C. And chapter 9 deals with, at the heart of chapter 9 is again structure of molecules, but this time we are talking about 3D structure. So Lewis structures were 2D structures. Based upon Lewis structure, another theory was built upon it, which is called VSEPR theory, which is valence shell electron pair repulsion theory, and it has 3 main important points. The first point is the electron pairs tend to be as far from each other as possible in the 3D space, in 3D region, giving each molecule a specific shape. Second thing, the bond pair repulsion is lesser than a bond lone pair, which is lesser than lone pair. So 2 lone pairs repel each other the most. Last point, single or double or triple bond are treated just as one electron domain in VSEPR. Now with these basic things, there are all the VSEPR shapes. Remember, AB3, AB2, AB2, AB3, AB4, AB5, and AB6. Please refer to the big table that we had drawn, and then you start getting lone pairs. So you get AB2E, here you get AB3E or AB2E2, here you get AB4E, AB3E2 or AB2E3. Okay, so Here you can get AB4E2. That's the one that we generally focus on. One thing I want to remind you here is you can determine the polarity of a molecule based on VSEPR structure. If it is distorted, generally it will have polarity. If lone pair of electrons are present on central atom, generally it has polarity because of distortion, except in the case of AB2E3. Even though it's got 3 lone pairs on the central atom, it is still non-polar because the 3 electron pairs that are present, they cancel out effect of each other. They are symmetrical around the central atom. That's why this is non-polar. The last part in the VSEPR structure is sigma and pi bonds. And remember guys, sigma and pi bonds, so sigma bond can be between anything, SS, SP, PP, SPS, SP, SP, any of the hybridized orbital. The only requirement is this is overlap along x-axis. Pi bonds rather specific. Pi bonds are formed as double or triple bonds. So the first bond is always sigma. The second and third can be pi bonds, and pi bonds can only be formed by unhybridized p overlap along y-axis. And talking about hybridization, hybridization incorporates 3D structure using VSEPR theory and explains it in terms of sp, d, and f orbitals. So hybridization is sp, sp2, sp3, sp3d, and sp3d2. And the last thing I want to talk about here is delocalization in context of C2H2 molecule. So if you had to draw its hybrid diagram, how would you do it? So think of it as, first of all, draw it as C2H2. So this looks structurally like this. So this is 2 half mirror images of each other. So you know this is sigma, this is pi, and pi. You know only sigma bonds are hybridized, so there are 2 hybridized bonds around central atom. So what hybridization is it undergoing? sp. And then these are pi bonds, so carbon has sp hybridization and sp hybridization. This hydrogen overlaps on it with the s orbital. How do we know with s orbital? Because the valence electron of hydrogen is an s orbital, and then it's got 2 unhybridized p orbitals, and then on the other side you have similar structure, and the carbons sp and sp overlap, and then hydrogen, and then you have 1 pi bond formed between y overlap and other pi bond formed by x overlap. Please go over the notes, we did it in detail. So what is delocalization in that context? Delocalization of electrons is when electrons are not present between nuclei of 2 atoms, but they kind of move about so that the electron density is spread out. Anything that is delocalized is generally more stable than non-delocalized. How can you figure out delocalization? Anything that shows resonance will have delocalization. So if it is a traveling double bond, it will be delocalized and be more stable. And chapter 25, I would recommend that you please go over from your notes, because it's already in very condensed form. Otherwise, Unit C's review is going to be very, very large. Thank you guys for listening, and that's the end of Unit C review.